Today's daily LeetCode problem of the day is find the city with the smallest number of neighbors at a threshold distance, number 1,334. For this problem, there are an n amount of cities numbered from 0 to n-1. We are given the array edges, where edges of I contains from, to, and weight, and it represents a bidirectional and weighted edge between a city's from and to, and given the integer distance threshold. We want to return the city with the smallest number of cities that are reachable through some path and whose distance is at most distance threshold. If there are multiple such cities, we want to return the city with the greatest number. So we have to notice that the distance of a path connecting the cities I and j is equal to the sum of its edges, weights along the path. So what does this mean? Our goal is to find the most isolated city and the one that can reach the fewest cities within the distance threshold, within our integer distance threshold. If there's a tie, we are going to choose the city with the highest number. So in this example, edges gives us 0, 1, 3. This means city 0 connects to city 1 with a distance threshold of 3, with a weight of 3, sorry. So 0 to 1 with a weight of 3. City 1 connects to city 2 with a weight of 1. So 1 to 2 with a weight of 1. 1 connects to 3 with a weight of 4. 2 connects to 3 with a weight of 1. Our distance threshold is 4. So the output for this solution is 3. And the explanation is the figure above describes the graph. The neighboring cities at the distance threshold 4 for each city are, so if we start at city 0, we can reach city 1 and city 2 without going over our distance threshold of 4. If we start at city 1, we can go to city 0. From city 1, we can go to city 2. And then from city 2, we can go to city 3, all without going over our threshold. Then for city 2, we can start, if we start at city 2, we can go to city 0, so up to 1 over to 0. We could go to city 1, or we could go to city 3 without going over our threshold. And starting at city 3, we can go to city 1 and city 2 without going over our threshold. So city 0 and city 3 both have 2 neighboring cities. So we want to find the most isolated city. So they both have 2 neighboring cities at a distance threshold of 4. But we're going to return 3 because that is the bigger number. So 3 can connect to 2, and it can connect to 4, or it can connect to 1 before going over its threshold. Because if we go from 3 to 2, 2 to 1, 1 to 0, that would be a threshold of 5. So 3 can only connect to 2, and 3 can only connect to 1. So it has 2 neighboring cities. 0 could connect to 1, and it can connect to 2 before it goes over its threshold. So between 0 and 3, we're going to pick 3 because it has the greater number. So how do we implement this? The best way to implement this is through a graph algorithm called the Floyd-Warshall algorithm. If you are unfamiliar with the algorithm, I suggest that you look it up and learn about it. But the intuition for this algorithm is it finds the shortest path in a weighted graph with positive or negative edges, as long as there's no negative cycles in the graph. Unlike an algorithm that computes the shortest path from a single source, the Floyd-Warshall computes the shortest path between all pairs of vertices in the graph. So the algorithm fundamentally takes a different approach by computing all pairs of shortest paths in one go rather than separately for each source. So we initialize our distance matrix, and then we find the direct connections between cities and fill their edge weights. Then all other distances are set to infinity. The distance from a city to itself is 0, and the matrix serves both as our working space and our final result. The core of our algorithm is going to be 3 nested loops, so it's going to have a time complexity of O of n cubed. The outermost loop is going to iterate through all vertices, and then for each potential intermediate point on the shortest path between each of other pairs of vertices, we're going to check if it passes through the current index or the current vertex. If it does, it can offer a shorter path that we currently know. Otherwise, we're going to update the distance. So this process gradually refines the shortest path By the time all the vertices have been considered, we have determined the shortest path. After running this algorithm, our distance matrix will contain all the information we need, and we can directly count reachable cities for each source and then select our answer. So the Floyd-Warshall algorithm has a significant advantage in this kind of problem, as it solves all the pairs shortest paths directly with a simple one-pass implementation. For a dense graph, it's better, and it will be done in O of n cubed, and it can be more efficient than other algorithms for a dense graph. But for less dense graphs, where only a few sources are involved, it can be less efficient. So how do we implement this algorithm? So I have a couple of comments up here already. First thing we're going to do is define infinity as a large constant value, and it's going to represent the distance of initial comparisons. Then we're going to create a 2D array called our distance matrix, and it's going to store the shortest path between each pair of cities. Then for each city, we're going to set the distances in the distance matrix to the infinity value, and then set the distance from city I to itself as 0. Then we're going to iterate through each edge in edges and extract the start, end, and weight from each edge. We will then update our distance matrix and the distance matrix start end and the distance matrix end start with the weight value. We will then call to our Floyd function, and it will compute the shortest path between all pairs of the cities. We want to return the city identified by calling a new function, and it will see the fewest numbers of reachable cities within a given distance threshold. So for our Floyd function, we're going to have 3 nested loops to update the distance matrix. The outer loop will iterate over each city, middle loop will iterate over each source city, and the inner loop will iterate over each destination city. For each combination of cities and intermediate cities, we want to update the distance if a shorter path is found. For our function that's going to update the shortest path, we're going to initialize the city with the fewest reachables to -1 and fewest reachable count to n. So for each city, we're going to count how many of the cities are reachable. For each city j, we're going to count the shortest path matrix if it's less than or equal to our distance threshold. And then we're going to increment our reachable count if city j is reachable in our threshold. So it's confusing, but we'll implement it step by step. If you want to follow along with the editorial, they have a good explanation of the Floyd function as well. So, first part, we're going to initialize a value infinity. So int infinity is going to be equal to an integer, and it's going to be of length 1e9 plus 7. So the largest value we could possibly store. Then we're going to initialize our 2D matrix. That's going to be our distance matrix. So integer array, 2D array, distance matrix is equal to a new integer array where both are of length n. Then we need to initialize our distance matrix. So we're going to initialize everything to 0 except if the two values are the exact same. So for int I is equal to 0 as long as I is less than n, I++. We're going to do arrays.fill. So we're going to fill the entire array of distance matrix of I with our infinity value. We will then go through and go to distance matrix of I, and that will be equal to 0. So the distance to a city from itself is 0. Every other city has an infinite distance until we define the distance. We will then populate the distance matrix with the initial edge weights that we are given. So we're going to do another for loop for each integer array edge in our edges array. We're going to take the start value. So int start is equal to edge of 0. Int end is going to be equal to edge of 1. And int weight is going to be equal to edge of 2. And then we will then populate our distance matrix. So distance matrix of start of end is equal to weight. And distance matrix of end of start is also equal to weight. So we're making a 2D matrix filling in the weights between each city. And if a city does not connect to another, it will be equal to infinite. So after we populate our distance matrix, we now just need to find the shortest path between two cities. So that's where our Floyd-Warshall function comes in. So we're going to call to Floyd, and we're going to pass our n value, the number of cities we have, and we're going to pass our distance matrix. So let's initialize our Floyd-Warshall algorithm. So it's going to be a void function. It's going to be called Floyd. It's going to receive an integer n and a 2D matrix we can call distance matrix again. So for our Floyd-Warshall function, we are going to try to find the shortest path between all the cities so we can take note of that for future reference. So how do we do that? We have a triple nested loop, and it's going to iterate over intermediate cities, over start cities, and over end cities. So first we're going to do the intermediate cities. So for int k is equal to 0 as long as k is less than n, k plus plus. For this is the start cities, int I is equal to 0 as long as I is less than n, I plus plus. And then for int j is equal to 0 as long as j is less than n, j plus plus. So these are our 3 loops. And now we're going to update the shortest path from I to j through a point k. So our distance matrix of I of j is going to be equal to the math.minimum value of distance matrix of I of j distance matrix of I of k plus distance matrix of k of j. So what is this checking? Basically, this is checking if, so our distance matrix of I of j is the current value we have stored here based off of the direct. So let's say if we want to go from 3 to 0, the direct line between 3 and 0 doesn't exist. However, down here, we're going to mark down our 3 to 0 as either distance matrix of I of j, which is currently infinity. That's what we stored it as. Or we are going to store it as from I to k, so from 3 to 1, and then from 1 to 0. So the total is going to end up being 7. However, that is still less than infinity, what it is originally stored at. Another example is checking the distance between 3 to 1. So we want to find the smallest distance between 3 to 1. The initial value from 3 to 1 is 4. However, if we go from, so let's say distance of I of j is 4. Now if we go from I to k, where k is 2, so from 3 to 2 is 1, and then from 2 to 1 is 1, this distance is only 2 instead of 4. So that's the new smallest distance. So that is actually it for our Floyd-Warshall algorithm. Next, we're going to implement an algorithm that is going to find the city with the fewest reachable cities, that has the highest number and falls within the distance threshold. So it's going to return an integer. First, let's incorporate it into our initial function. So it's going to return get city with fewest reachable. We're going to pass it n, our cities. We're going to pass it our distance matrix that we just filled using the Floyd algorithm. And we're going to pass it our distance threshold, which is the limit. That's our limit on our distance. So it's going to return an integer. That is going to be the city. Sorry, just a second. So now we're implementing our algorithm, get city with fewest reachable, which is going to return the right city based off of what the Floyd-Warshall algorithm produced. So it's going to return an integer, and it's called get city with fewest reachable, and it's going to receive integer n. That's how many cities we have. Integer 2D array. Let's just put this on its own line. Integer 2D array. We could call distance matrix again, and then it's going to receive an integer distance threshold. Cool. So, what is this function going to do? It's going to find the city with the fewest reachable other cities based off of what was produced in our distance matrix. So first thing we're going to do is initiate a variable int city with fewest reachable. This is going to be our output, and currently it is -1. And then we're going to have an integer fewest reachable count. That's going to be equal to n. So the current fewest reachable cities we can reach is the entire, every single city. And the current city that can reach all these cities is non-existent. So it's -1. Now we're going to do a nested loop that is going to iterate over and find which city has the fewest reachable cities. And it's going to keep count of what the fewest reachable count is. So for int I is equal to 0, as long as I is less than n, I plus I plus plus. And our current reachable count is going to be equal to 0. So for int j is equal to 0, as long as j is less than n, j plus plus. If I is equal to j, we're going to just continue. So it's going to skip itself. We don't want to have the city count itself, so it's just going to skip it. Otherwise, if our distance matrix of I of j is less than or equal to the distance threshold, then we can increment our reachable count. So if the distance it takes to get from city I to city j is less than or equal to our distance threshold, we can increment the reachable count from the city I. Then we want to update the city with the fewest reachable cities. So if our current reachable count is less than or equal to our fewest reachable count, then we're going to want to update it. So our fewest reachable count is going to be equal to our reachable count, and our city with fewest reachable needs to be updated because we found a new lowest count, and it's going to be equal to city I. Then we simply want to return city with fewest reachable. So if we run this, passes our test cases, and if we submit it, passes all solutions. It should be a time complexity of O of n cubed. Submission length exceeds limit. And we can't check on LeetCode. Awesome. So let's go ahead and do this in Python. It should be the exact same, pretty much. First thing we want to do is initiate a variable infinite. It's going to be equal to an integer of length 1 e9 plus 7. Then we're going to have a distance matrix. I need to get used to using the underscores for names in Python. It's going to be infinite times n for each variable in range n. So that creates our 2D distance matrix. Then for I in range n again, our distance matrix of I is going to be equal to 0. So it's going to mark each occurrence of the same exact variable. So for each city from its distance to itself, it's going to initiate it as a 0. Then we're going to want to pull the start, end, and wait from our edges array and implement that into our distance matrix. So for start, end, and wait in edges, distance matrix of start of end is going to be equal to the wait, and distance matrix of end of start is also going to be equal to wait. We are then going to call to our Floyd function. So, sorry, I think I skipped over it, but in the distance matrix, we filled all the variables with infinite already. So we filled it with infinite for n amount of rows, for n amount of columns. So our distance matrix is full of infinites here. We then go through and fill all the occurrences of the same city with 0. And then we go for each start, for each end, we put the weight as the value. Now we're going to call to the Floyd function. So self.floyd. We're going to pass it n and our distance matrix. And then we're going to be able to return self.get city with fewest reachable. And that's going to receive our cities, our distance matrix, and it's going to receive the distance threshold. So let's define the Floyd function. So let's def Floyd. It's going to have self. It's going to have n. It's going to have distance matrix. And now we're going to simply update the distances for each intermediary, each city. So for k in range n, for I in range n, for j in range n, our triple nested loop. And all it's going to do is update distance matrix of I of j based off of the minimum value between distance matrix of I of j and distance matrix of I to k plus distance matrix from k, matrix from k to j. So again, all the Floyd function is doing is going through each, let's say k is an intermediate city. So if we want to go from 3 to 1, we either have the option of going from straight from 3 to 1, or 2 can be our intermediate city. So we could go from 3 to 2 to 1. So we're updating our distance matrix of I to j. So let's say I is 3, j is 1. Distance matrix of I to j is currently 4. So we're saying if distance matrix from I to k, so if k is 2, so from 3 to 2 is 1, plus from k to j, so from 2 to 1 is 1, so 1 plus 1 is 2, 2 is less than 4, so the new shortest path from 3 to 1 is through city 2. So we go from 3 to 2 to 1. That is the shortest path of length 2 rather than of length 4. And that's all the Floyd function is updating. And that is all we need from the Floyd function. We can now define our get city with fewest reachable function. So def get city with fewest reachable. That is going to receive self, it's going to receive n, it's going to receive the distance matrix, and it's going to receive the distance threshold. So for this function, all we have to do is increment through each city and find which one has the fewest reachable without going over the distance threshold. So we're going to have city with fewest reachable. That is currently equal to -1. There's no city we've determined yet. And the fewest reachable count is currently equal to n, because that is the total number of cities we have. We're assuming we could reach every city without going over our threshold. Now we're going to go for I in range n. For I in range n, our current reachable count will be equal to 0. Actually, the current reachable count is going to be equal to the sum of 1 for j in range n if I is not equal to j and the distance matrix of I of j is not equal to the distance threshold. So what is this doing exactly? So the reachable count is going to be equal to the sum. So we're going to add 1 for j in range of n if I is not equal to j and the distance matrix is less than the distance threshold. We're going to increment 1. So reachable count is going to add 1 for j in range of n as long as I is not equal to j and distance matrix of I of j is less than or equal to our distance threshold. That's all that's doing. We then want to update our reachable count to our fewest reachable count, as well as our city with fewest reachable if we find a new fewest reachable. So let's currently name this fewest reachable. So we're still going to be in this for loop actually. If reachable count is less than or equal to fewest reachable count So we're going through finding the reachable count for city I. So how many cities city I can reach within the distance threshold. Then if we find a new lowest reachable count, we are going to update that, and we're going to update the current city that has the lowest count. And we're using less than or equal to here to update the lowest reachable count, because in the case scenario where, let's say, city 0 and city 3 both only can connect to 2 cities, we want to return the highest number city. So it's going to update the most recent one we find, and we're going to find the highest city last. So if we run this, so this passes our test cases, and if we submit it, it passes all solutions. Thank you, and follow for more daily LeetCode solutions.